the organizers. Thanks very much for having me. I have no movies in this, so I now feel a little bit inadequate, but I may apply to that pre-doctoral program. Sounds awesome. Okay, so my name's Toby Brown. I'm from the National Research Council of Canada, and I'm going to be talking to you about some work I've been focused on over the last couple of years, looking at this question of how does environment regulate galaxy evolution, primarily through the gas star formation cycle. And all the work I'm going to show today is in collaboration with this Vertigo team. So this is the Virgo environment traced in CO survey, of which I am the PI. So to kind of orientate us and motivate the talk, I'm showing a real famous plot that I'm sure many of you will have seen, which is from Peng 2010, where they took SDSS galaxies and they plot stellar mass on the x-axis, some measure of environment over density on the y-axis, and they have hundreds of thousands of galaxies, so they can color this parameter space by the quenched fraction of galaxies. And the point I really want to make here is that you get this really nice two-dimensional gradient across this parameter space, which is telling you, well, I'm going to give you a broad, very reductive statement, but there are two main drivers of galaxy evolution. There's the passive, sometimes called secular evolution, which is primarily associated to the system's mass. And there's also the external influence from the environment in which the galaxy resides. And then the other thing I want to kind of plug into this picture is the gas. So you can think of this as kind of a third axis on this Peng plot. But if you look at, in this case, the atomic gas scaling relation, gas fraction scaling relation with the stellar mass. So this is for like 10,000 local galaxies. You get this really nice trend where it just tells you that, you know, smaller galaxies tend to be more gas rich and larger galaxies are more gas poor. But you can break that up in terms of the halo that the galaxy lives in, and you get this kind of monotonic decrease, this vertical separation here, where for a given stellar mass you have less and less gas. And so it's really, again, showing you these two effects, the kind of primary relation with stellar mass and then the second order effect with the environment. And that's, of course, what I'm focused on at the moment, but really the job is just disentangling the physics between the two. Okay, so gas, I've mentioned H1. Now I'm just going to talk generically about the ISM or gas, and really environmental processes act on galaxy evolution and star formation primarily by perturbing the ISM. And I'm just showing a nice cartoon from a recent review paper that gives two of the main mechanisms by which that happen. I'm sure you're familiar, but starvation is kind of the mechanism by which you just shut off the gas accretion and then consume the rest of the gas disk in star formation. And then you have active gas stripping, like ram pressure stripping, tidal stripping, this type of thing, that sweeps the gas from the disk, and you also shut off your star formation. And the point I kind of want to make by showing these two examples, not only are they common, but I would argue that they rarely kind of act independently of one another. So particularly ram pressure stripping, I would say that you basically can't have a galaxy that's stripped and not starved at the same time. And often the other case is true, where you get starvation, you also have stripping. Okay, so let's focus even more on the gas. So we're interested in how environment affects star formation. Of course, we have to look at the molecular gas. And people have done this, and we essentially see there is an impact of environment and environmental processes on molecular gas reservoirs. But so far, studies have really been limited to kind of global properties and also resolve very detailed, spectacular studies, but of very small numbers of objects. So what we have here are just kind of examples of each. These are two resolved studies that show nicely on the right that you have longer depletion times in the red points, which are cluster galaxies, than in the field of the group environment, which are down here in the blue. I also am showing this plot from Baselli, which introduces nicely this gas deficiency parameter. So for those of you that aren't familiar, this is, in whichever gas phase you're interested in, this deficiency parameter just says, how gas poor am I with respect to some field control? So if you're kind of to the right on this, you're very gas poor. And the same is true for the molecular gas here, and they're showing for cluster galaxies, there's this nice relationship between the two. So molecular gas is being impacted. And we can see this from a resolve perspective as well. There's this spectacular work by Kramer in 2019 that is showing a ram pressure stripping event going on here. So you have HSD in the background. You have the dust lanes in absorption being lifted out the galaxy, the leading edge along here. And then you have in the green is the molecular gas. And you can basically just see right away it's being stripped as well. And this is from the GASP survey on the right that show that there is longer depletion times in the stripped gas in tails than there is in the field or in the remaining gas in the body. Okay, so that's kind of the state of play. And this is where we come in. I would argue, and I think that there's a reason a lot of the results I've shown so far are from the Virgo cluster. And I would just say that the Virgo cluster is the ideal laboratory for studying these kind of mechanisms and for the impact of environment on galaxy evolution. And the reason really is that it's a really massive galaxy cluster, so over 10 to the 14 solar masses in its halo mass. It's relatively nearby. In fact, it's the nearest massive galaxy cluster. It's actively forming as well. So a lot of the galaxies that are in the Virgo cluster are undergoing these transforming mechanisms. And basically, because of these facts, you end up with a cluster that just has completely unparalleled multi-wavelength coverage. And this is what we have done to kind of contribute to this picture and to add to the multi-wavelength coverage of the Virgo cluster. So we have this ALMA Cycle 7 large program where we observe 51 galaxies in Virgo with CO 2:1 maps at around about 0.5 kiloparsec resolution. For the chemists among you as well, we also have dense gas tracers in these isotopologues, and we're broadly focused on these questions, but of course there's a lot of sub-questions in there. And for those of you that are really interested in the details, speak to me. Well, the survey paper is Brown 2021. Okay, this is an example of the CO data that we have for all of these galaxies. So this is just a fairly boring vanilla galaxy that isn't so affected by its environment, a little bit truncated maybe. But on the right here, you have the integrated intensity, or you can convert this to a molecular gas surface density. We also have exquisite kinematic information from the cold gas, which is super useful. We have a PhD student working on kinematically modeling all of these galaxies. And then on the right here, this peak temperature nicely traces the gas morphology. But of course, because we have this really well-surveyed set of galaxies, we can also derive stellar mass density maps, star formation rate surface density maps. We have H1 density maps for all of these galaxies. And we've also just begun a MUSE large program to go and get MUSE data for all of these systems. Well, for 40 of the 50. Okay, so some results. So we can move away, obviously, from these global studies, but we can still do kind of statistical type studies looking at the radial profiles of CO in these galaxies. And so what you can see here, this was work done by Nikki Zabel, who is now a postdoc in Cape Town. And Nikki shows really nicely that when you compare the CO profile of galaxies that have been in the cluster for a long time, so that's this purple line, with galaxies that are either in the field or have just fallen into the cluster. So this is the green line and the yellow line. You see that for a given radius, they're depleted in their molecular gas content, but also it's preferentially affecting the outskirts. So you have this basically outside-in removal or suppression of molecular gas. Work by Vicente Villanova in University of Maryland took this kind of another step by plugging in the atomic gas to look at the ISM composition. And Vicente shows really nicely that when you look at the ratio of molecular to atomic gas in these different galaxies, you can bin those galaxies by their H1 morphology into different classes, basically. So you show for cluster galaxies that have just fallen into the cluster, these are unperturbed, then you have asymmetric, and then you have truncated. So they've been in the cluster maybe a couple of pericenter passages. You see that the ratio between atomic to molecular gas increases as a function of environmental influence. But the question here is this kind of ISM condition differences between the two samples? Is this driven by environment? What's going on? And so this was really nicely investigated by Adam Watts, who's a postdoc in Australia, in ICRA in Perth. And he looked at this same ratio, this R-mole, as a function of a proxy for the midplane pressure. And what he shows, these are just 4 representative galaxies, but he did it for the full sample, that for a given midplane pressure, you can compare the actual galaxy to what you would expect were it in the field versus what you would expect were only H1 removed during the stripping process. And you can see that it doesn't match in many of these cases with either one of those lines. And so what you have here is that you must be stripping the molecular gas and differential stripping between the H1 and the molecular gas to result in this, basically this ratio for a fixed midplane pressure. Okay, so, and now we come to some work that I recently submitted. We have all this multi-wavelength information on the star formation rate and the stellar masses, so we can look at the typical relationships that people examine in this parameter space, but fold in this environment angle. So this is a very common relationship in these resolved studies. It's sometimes called the resolved star forming main sequence. And it's just stellar density versus star formation rate, surface density. In the gray background here, I have a field sample, and then I do a similar split. I take this H1 deficiency parameter and I say, okay, in blue are all my H1 normal, so not so affected, and in red are all my H1 poor, so pretty affected by or they've been in the cluster longer, let's say. And you can see that the H1 poor are offset to lower star formation activity, which is kind of interesting, but not in and of itself unexpected. We can show this really nicely, that this is a pure result of them having less gas. So we have this is sigma star here, and again they're offset in this relationship to lower gas content of fixed sigma star. And you also have longer depletion times or lower star formation efficiencies, however you kind of frame that, when you look at the Kennicutt-Schmidt relation as well. Now the question is this due to environmental mechanisms? This kind of double whammy of less gas and also longer time for that gas to form stars, causing lower star formation activity, is it being driven by environmental mechanisms? So, fortunately, one of our kind of team members back in 2017 took these galaxies and she classified them using a combination of H1 morphology and phase space into these different, let's call them kind of cluster infall stages. So you've got unperturbed galaxies undergoing early ram pressure, then active ram pressure, and then galaxies that have been through and been stripped. And then these anemic disks. So these are truncated, so they've likely had some stripping, but they've also undergone starvation. So they've got low density H1 disks. And you see it correlates really nicely with the sequence correlates really nicely with this H1 deficiency parameter, which gives you an idea that you're probing these processes when you divide the sample in this way. We can go a step further and basically subtract off these main relationships, this Kennicutt-Schmidt relation, the molecular gas main sequence, and the star forming main sequence. We subtract those off to get for each pixel within the galaxies some measure of how gas rich they are and how efficient at forming stars they are with respect to the median. So, and then you can play these types of games, looking at the distribution of these properties as a function of the infall stage. So what we can show here is that you get this kind of nice sequence of kind of being more and more quenched as you fall into a cluster. And particularly, you see in the post-ram pressure stripping stages a real clear signature. I should say we split them into inner and outer disks. And you see this signature of outside-in quenching. We also see this in the gas as well. Sure. I mean, I'm almost done. We see this in the gas, so that the gas is actually, driving this decrease in star formation. And we also see kind of, to a lesser extent, but still there, the signature in the star formation efficiency or the depletion times as well. So we have, again, as a galaxy falls into a cluster, this combined loss of gas and also reduction in the efficiency of which it forms stars is hammering the star formation rates. The other thing I want to point out here is that in this anemic disk class that, just to remind you, has been stripped and also starved, you don't get the differences between the inner and outer disk. So this is telling you that starvation is actually really effective at quenching the remaining gas disk after the outskirts has been removed. And then the kind of interesting result that popped out of this is that we observe elevated gas densities only in the earliest stages of ram pressure stripping. And that feeds through actually into the star formation rates. And this has been reported before, both in models and in observations. And there's always been that little bit of tension there between these observations that show maybe elevated ridges of density in some ram pressure strip galaxies versus the fact that overall this is clearly a quenching mechanism. And I think basically what's happening there is that observations that do show this are capturing this early stage of stripping. And so I think I will kind of wrap up there and just to quickly run through a very brief summary. We show that environment-driven molecular gas depletion occurs throughout the galaxy disk and is important for your kind of models and your consideration when looking at how environment quenches galaxies. A really nice result that popped out of a couple of papers is that you have environmental processes actually altering the composition, this ratio between molecular and atomic gas in the ISM. And then we see this sequence of stripping that leads to quenching from the outside in. And I will just leave it there and happy to take any questions. Thank you.
All right, time for questions. Peter?
Peter Bruzi, where are these galaxies in phase space? So I'm wondering if you can say something about when ram pressure stripping starts happening relative to the cluster radius, if you look at where these things are in the position and velocity space of the cluster.
Right. So, I mean, they're where you expect, with the caveat that the 2D projection of phase space is never clean. So you see these, where should we go? You see the galaxies that enter into this ram pressure stripping phase falling in towards the center of phase space, but the velocity is going up and up. And then, yeah, perhaps backsplash galaxies in this post-ram pressure stripping stage and so on. So they lie where you would expect, given some tolerance for, the smudging out of this 2D projection effects, basically. Yeah.
Hi, this is Francisco Castander. What is the information you use to do that classification?
For the stages on the left, so it's a combination of phase space and H1 morphology. So we have big H1 maps for all of these galaxies. Yeah.
Hi, Jessica Starkmark. Do you have a sense of why the star formation efficiency is changing?
No, that's what Kartik and I have been trying to figure out while we're here. So I think that's the key question next. And actually, I've kind of presented quite a strong version of it that it is being driven by environment. And work this week has actually made me question whether that's actually the case. Thinking about all what's going on, like transitioning gas densities, I don't know. Anyway, basically the answer is I don't know, and that's my next paper, is to try and figure that out, because I think it's key.
I have another question, but if anybody else is, okay. Yeah, so I wanted to ask about the enhancement in the gas density for early stripping. And I'm wondering if that's also happening later in the stripping, but because you've already stripped. It's like you get a enhancement closer and closer in, but because you've also stripped part of the gas, in the end there's still less gas. But that the enhancement is effectively, it's like this physical mechanism is still happening. But you just don't measure it if you look at the total gas.
I think we wouldn't see it in this. So, but we have the data to go look for that.
Yeah, you have the data to look for like density profiles and things like that.
Yeah, exactly.
Cool.
Yes.
Any other questions? So let me ask one. So have you cross-checked with other surveys, say like X-ray surveys, and if the footprints overlap and see increase in the gas temperature, and especially the hot gas, with its entering of these clusters?
Well, not exactly with the temperature, no. And I think you still fall down on this 2D projection. So we have like galaxies that are clearly, when you look at their H1 content, are like in this unperturbed stage, right? They're just falling into Virgo on first infall, and they're bang smack over the center of the cluster. And we can't get around. I mean, I wish I could like turn it around, but I can't. So my feeling with that is that you get hammered by the projection effects and you wash out the signal. Because, to first, and also Virgo is like non-virialized really, and it's hard work. But so you wash out a lot of those effects. Like the simplest thing to do is to look at like distance from cluster center, and we see very little impact of like environment when you just use distance, like projected distance to cluster center. And I think it's purely because you're mixing your samples.
Thanks.
Yeah, Suchatakure. So I wanted to know if you subdivide them according to integrated stellar mass bins.
Yeah.
Will you see a difference? For example, the H1 deficiency and so on.
Yes. So good question, and that's in the appendix in the submitted paper. We do this. So the signal remains when you control for stellar mass, basically.
And how big are these? The most massive galaxy?
We kind of go from 10 to just below 10 to the 9 to 10 to the 11.
Okay.
Stellar mass.
I'll see. And then also another question is, how about the inside-out quenching scenario, and how does that play into this picture?
So yeah, I mean, so the short answer is the Muse data will help a lot more with this, and that's probably where I would leave that. So I mean, we're still in kind of the early stages, and we're looking at the major signals, but yes, these galaxies have been through pre-processing, and there's some like signatures of pre-processing before they enter the cluster environment, and then you see truncation of the gas disk and so on. So it's like disentangling them is non-trivial, and I think the Muse data will help a lot with this.
Just a short follow-up. The signature that you talked about with the stellar mass, does it increase or decrease?
It decreases slightly, but still significant. Yeah, there's actually quite a weak trend between H1 deficiency and mass because there's a control sample here. So H1 deficiency is actually calculated for a given size and mass of galaxy. Does it have the gas you expect? So you wash out a lot of the trend with stellar mass. Excuse me.
Just Starkmark again. So basically you expect that like the position of the galaxy in these planes and how deficient it is in H1 and in molecular gas and in star formation, you expect it to correlate with its trajectory through the cluster?
Yes, I would say so.
Basically, it's past trajectory in the cluster.
It's what trajectory?
Past. It's like, what is it? Is it just on first infall?
Right, exactly,
Where
like
is
the
it?
cluster info history.
Has it been gone?
Exactly.
Has it gone through, and is it on its way out?
I don't know the fidelity by which you can trace that back.
Yeah. So my question would be, how much information do you think there would be in the sample? Do you think that information could be used to learn about the mass distribution of the cluster? Right.
So that's something we're working on with Adam Stevens, so he has extracted this sample from illustrious TNG, and then I'm going to talk to him.
Any other questions? We still got plenty of time. But if not, let's thank Toby again.